All right. So I think that our idea of charge is an approximation, and it is not accurate. It is not an accurate description of what is going on. Um, you wouldn't describe your attraction to a spouse as positive or negative, would you? Um, having a positive attraction or a negative attraction to a person. Um, okay. That having a positive or negative attraction to a person, if you called that spinning, if you said you had an attraction to a person as spin up, and if you didn't like them, that spin down, right? Um, uh, that's I kind of confused myself there because I tied in two things here, but I'm going to go with it because I still stand by what I'm saying. So if you describe that your attraction is these two things, um, that that is correct. It does describe what's happening, and as long as you know what is happening and you call it that, then you're technically correct. But that's not really, that doesn't explain the reason behind it, and it does not truly explain why you feel the way that you do, right? It's just kind of a placeholder for everything that you do feel, because we know that when you do feel this way, you know, you're attracted to them, and we observe this attraction, and then we observe no attraction when you don't like them, right? So, um, it may not be a one-to-one comparison, but I do think that it is comparable, because we don't really know, we don't know what is happening on the like scales of these particles, right? So when we describe something, we're just kind of describing the behavior as best as we understand it, but it's not, getting the full picture. At least I don't believe it is. And so, the fact that charges exist even in quarks, or quarks are, and which you know build up like neutrons and protons, and show us that having fractional charges means that we assume, that they have like these fractional charges because it works for our calculations and stuff. But that doesn't necessarily mean that that's what's going on. That's not necessarily the full picture there. And I think that we should kind of dive deeper into these, I guess, reactions and approximations that we've made, because at this point they're just a given in our calculations and stuff. But when we simplify everything down, we lose a part of the data, a part of that information. And I think that doing that is hindering our ability to understand further. Because when we want to basically approximate a signal, right? The actual signal is a perfect curve, right? But in order to approximate it, what's done is we just do like rectangles, basically, like 90-degree angles, and we do it to a high degree, right, to get a very it's a smooth looking curve, but there's still just so much data that's getting shed off of that curve in order for us to approximate it, right? And, you know, we can assume that we're getting most of the data, and so our calculations are correct, and so it's all good and no worries. But data is still being lost, and I think that that could be an issue. And so I think we should maybe look back at some of these things instead of assuming this simplistic behavior. We maybe look into why it acts this way and see if we can define it better. My camera died on me on that one, and my camera died on me on that one. But I think that we should define it better. I think that's what I was saying. So yeah, I think that there is there's more there, and I think that we should look at it more. I have some stuff that I will eventually talk about. I will get into it, but I won't get into it in this one. I just kind of want to get the point across that I think that looking at things as this simplistic charge, and setting it as a set value is it's not right. I don't think that these charges are necessarily constant. I think that they might vary, and I think that looking at everything as, oh, the neutron is neutral and the proton is positive and the electron is negative, and basically setting those as their value is always -1, their value is always +1, their value is always 0. Setting these like definites, even if we've got experimental data to, support it, I don't think it's necessarily right, because just because we have data that tells us that we're right doesn't necessarily mean that we are. If you ask 50 people that like pizza if pizza is good, right, you're going to get the answer that yes, pizza is good because they like pizza. But if you were to ask 50 people that don't like pizza, right, and you ask them, is pizza good? They're going to tell you, no, pizza is not good. They don't like pizza. And so just because you have results that are confirming your theories, it doesn't necessarily mean that your theories are correct. It just means that you haven't asked a person that you haven't asked I guess, a diverse enough audience or the right questions, because you are getting the same results, but I I think there's certain parts about the atomic model we currently have that don't quite make sense, and it goes into the whole strong force, and it's like, oh, and these forces are just so strong, and then that the strong force is holding this nucleus together, and then once it gets too big, then the strong force no longer can hold it in, and then boom, it releases off stuff. And I don't necessarily think I agree with that description. I don't I think that if neutrons were neutral, right? If they were truly neutral, then why would they not just be floating around on their own more than not. And why wouldn't there be just clumps of neutrons? Because if there's no reason, there's no, if they're neutral, right? There's no reason for a proton to, necessarily bond with it, right? If they're just neutral, there's no reason for it to bond with a proton. There's no benefit there for the neutron. To my understanding, from what the current model is, I don't see a benefit other than we know that it makes it more stable, right? So we're saying, oh, well, the neutrons help hold the nucleus together by stabilizing it, right? And it's like, okay, but why? And that's kind of the stuff I want to get into. And I have a theory of my own that I've been working on, but it's just kind of that when we define terms and we set them as, certain, we no longer question them. And when we no longer question them, right, and we find that we still don't truly understand why things are happening, but we're certain on terms, that's when we start to go back and look at terms that we are confident in and put them through more rigorous questions. It's like, okay, well, and like I said, maybe there is a well-defined theory that is basically exactly what I'm thinking or is better, but from what I've seen, it sounds more like we just say, well, they, are there and they're kind of like the glue of the nucleus and they help stabilize the proton, and it doesn't really explain why we can have like so many neutrons added onto a nucleus, compared to how many protons, right? It doesn't really give a good explanation why we can handle it, like a nucleus can handle so many neutrons, right, compared to protons. Like, it doesn't, I don't really see like with our current model talking about the strong force, right? Basically, we say once the nucleus gets too large, it no longer can attract. The strong force no longer has power over, those neutrons, so more neutrons don't join the party, basically. And I feel like that is not good enough. Saying, oh, the strong force just can't hold on to it anymore is not good enough, in my opinion. So yeah, my goal is to reduce the amount of fundamental forces. And I think that they can pretty much be boiled down to basically one, maybe two. But we will get there. So that's all for this one. Peace out.